Most students have worked with optimization problems of the types we've been looking at, with either simpler or more complex. One thing you may not have seen, though, is this new kind of variation, which is very, very common in practice when you're using calculus in the sciences and economics. The issue is there might be a range of values. We don't necessarily know, in this problem here, all the velocities that we might want to know. In particular, we're going to work with the idea that the speed that the Fisher person can walk, is still going to be at 5 kilometers per hour, but that we don't know the speed at which they can row. One of the things we could ask is, at what velocity will it be best to simply go straight to the lighthouse? Let's take a look at what we mean here. We know that when the velocity was 4, it helped to cut off most of the distance and land at 8/3 and then walk the little bit at the end. If we increased our water speed by just a hair, though, it might be beneficial to land even closer. And there's going to be a velocity at which we could go straight to the lighthouse and not lose any time. We know it's certainly going to be at 5 or less, because if we can row and walk at the same speed, we might as well just row in the shortest possible path. But it might be that even if we row slower than we can walk, it would still be best to go straight to the lighthouse. Okay, that's the challenge. How do we work that into the kind of calculations that we do with critical points? We're still talking about an optimal value, but it's going to depend on v. So the optimal x depends on v. In fact, we found that before because we know what t of x is. It's the square root of 4 plus x squared over, it was a 4 here before, but now it's going to be a v because we don't know what that speed is. We still have the same term for the travel time on shore. And again, we keep our domain x being part of 0 to 3. Okay. This takes a little mental gymnastics, so follow along if you can, as best you can. What we want to find is a v. We want to find the v, and you can imagine as we gradually increase v, as we gradually increase the speed, the optimal landing point is going to move further and further towards the lighthouse. At some point, when we increase v enough, we will reach that point where it's best to go straight to the lighthouse. So what we're going to be setting here is we want to find v such that the critical point of t of x is at x equals 3. So it's a bit of a reversal from what we just did before. We want a critical point, yes, but we're going to set what the critical point is and solve back for v. In the last problem, we had v, it was 4 kilometers per hour, and we solved for the critical point. So it's just a reversal of what we did before, but it may take some thinking about to see why that makes sense. If it does make sense, let's move forward. Our t of x, again, is square root of 4 plus x squared all over v, and then we add in the travel time on shore, and we know the derivatives of this already, except with v's instead of 4's. Our derivative is going to be 1 over v, 1 over 2, square root of 4 plus x squared, times the derivative inside is 2x, plus 1 over 5 negative. And we get to cancel our 2's here. All right, so we want a critical point. So we're going to set t prime equal to 0. And at the same time, we want the critical point to occur at x equals 3. So we want this to equal 0 when x equals 3. That's going to give us a whole new equation with values filled in. We don't know what our speed is yet, but we do know that we're going to have 3, that x up top, divided by 4 plus 3 squared minus 1/5. Okay? And now we're going to solve for the velocity that gives us x equals 3 as our best landing point. So solve for v. We'll bring that over. 1/5 is 1 over v. 3 over 4 plus 9 is root 13. We'll bring the v up and the 5 over. V is going to equal 15 over root 13. And that is approximately 4.16 kilometers per hour. All right. Does that make sense? That's the real question in these kinds of problems. Have we done something that's reasonable? Remember that when we moved at 4 kilometers per hour, it was good to land very close to, but not at the lighthouse. As we speed up, it's better to spend longer on the water than on shore. And so if we just increase our speed a little bit further, it's entirely reasonable that it would be best to go straight to the shoreline. If we had a much slower speed, we should cut out the water, but just a little bit faster than we went in the first example makes sense for something that'll lead to the fastest speed being directly towards the lighthouse. So we have confidence that this value makes entirely reasonable sense in the problem. Just be aware of how we arrived at that, because some of the problems that we look at in all exams will also have this same secondary follow-up question to them.